Welcome to the second tutorial in the SIDD online tutorial series. In the first tutorial we loaded SIDD onto a new workstation. In this second tutorial we'll be walking through the steps involved in setting the model parameters up to run a new simulation and looking through the model output. Now you might recall from the first tutorial, if you actually looked at that we loaded the model up into the temp directory within the C drive on this workstation here, and we discussed all of the files that the model installation actually produces. One of those key files is a Lynda user manual. If you didn't look at the first tutorial, it is important to note that SIDD is like a model framework for conducting dynamic, structural dynamic microsimulation model projections. And Lynda is the UK parameterization of that framework that we're working with at the National Institute. Now, just as an overview, the first tutorial walks through effectively section 2 of the user manual. In this tutorial we'll be walking through section 4, altering model parameters, but we'll be doing that very briefly. Section 5 and section 6, so running the model on a local computer and looking at the simulation output. If you are looking for additional detail about anything that is discussed during this tutorial, I encourage you to look at the user manual as your first port of call. So let's get into exactly what it is this model, or how it is this model is set up, and what it actually produces when you run it. Now you should think of, well, all of the files that are necessary to run the model are found in this model subdirectory that is loaded onto your computer as part of the install package. And within that subfolder, subdirectory, you'll notice there's a whole bunch of files. And this might be somewhat intimidating when you first come to look at it, but it is, I think, fairly straightforward. The key thing to look for in the first instance is this job file, Excel spreadsheet, and this is really, if you like, the control panel for the model. So if we open that up, this Excel file takes a very discrete structure. The input, there are a series of sheets along the bottom here. The last two you shouldn't touch. They're just part of setting the parameters up. The first three, in contrast, you're likely to be working with from time to time. Now the input sheet is the sheet from which the model loads in all of its model parameters. Okay, that's the place that the model looks. The input A sheet is, in contrast, a comparison with the input sheet. Now the SIDD microsimulation structure is really designed to perform comparisons between alternative counterfactuals, policy counterfactuals. The input A sheet is assumed to store all of the parameters associated with your base policy environment for comparison. Okay, so the model assumes that it's running a simulation, and that simulation effectively, in general, will be compared against an alternative simulation, and the parameters for that alternative simulation, what we refer to in general as a base simulation, are stored in this input A sheet. To help you make comparisons between the input and the input A sheet, there's this check sheet. Now the check sheet includes a sum of all differences between the input and the input A sheets in cell A1. Otherwise, all of these zeros along the top in red are the sum of values in the respective columns. So if, for example, we made a change to column J, row 26, we made that 1. Well, actually, that was a bad idea. J53, and we changed the value 0 to 1. And we made a change again on Y32, and we changed that to 3. If we go to the check sheet, you'll see that there's a value 2 now. There's a number 1 in cell J1, indicating that there's 1 difference in the jth column at row 53. That's the first change that we made right here, row 53 relative to 0. And again in column Y, row 32, there's a difference there which we added. Column Y 32, the value is 3, and it was 0. So that's how you find differences between your prevailing parameters, the parameters that you have at the moment, and the respective base parameter specifications. Now, looking at the input sheet, you'll see that there's literally a sea of parameters here, and finding the right parameter to alter to achieve a particular policy specification can be, well, at least in the first instance, is likely to be an impossibly daunting task. And for that reason, we've added in a bunch of Excel user forms to guide you through altering the parameters that are likely to be of key interest. Before we get into the user forms, it's worth just noting the nature of the way that these parameters are set up in the input sheet, primarily because with use you may well find, and indeed as is the case for us in the developmental team, that altering the parameters directly in the spreadsheet can be a lot easier, and indeed there are a lot more parameters in the spreadsheet than can be altered in the user forms, and for that reason there's a lot more flexibility provided in altering the parameters directly in the spreadsheet. So you may well find that this is a place that you're likely to want to affect changes. So to help you do that, there's a sort of a color coding scheme that is imperfectly implemented in this model, in this spreadsheet structure. Red numbers are typically on-off switches. A value 0 is off, a value 1 is on. Pink numbers tend to be age-specific numbers. So, for example, forced retirement age after age 74, start age 18, lifespan 130, debt paid off by age 70, and so on. Blue numbers are numbers that are just model parameters. They could take a value of anything, really. And then there are some green ones which are really primarily utility preference parameters, but they do include some other key subjects of interest. For example, the total size of the data set that's loaded in, from which model projections are made. So that's a very brief overview. You should note that that labels for the different parameters tend to be provided in the columns just before the respective parameter. So the lower age for limited analysis, that's not very descriptive. Debt paid off by age 70. In contrast, the only difference being for the parameters in columns G through W, where these are age specific. So the title is up the top, and then each parameter it applies to a different age. Finally, if you are in doubt about what a particular parameter does, often there are comments that are provided on key parameters to provide a little bit more detail about exactly what that's going on. But for the moment, let's stick primarily to the user forms. Now, the user forms to use the user forms, you need to enable macros in this spreadsheet. How to do that is outlined in the user manual. I'm not going to discuss that just now. Once you have enabled macros in this spreadsheet, you should be able to hit Alt and F8, which will bring up a macro box. And we're looking for the SIDD macro in this list here. And just hit Run. And that will bring up a Form 0, basically an Excel user form. And these forms, you can just enter new parameters into boxes. There are buttons to press. Hopefully, it should be all fairly self-explanatory. One key issue to note here is this these names. Let's step into the first user form. If you want to alter the model parameters, particularly for the UK, for which this front end is primarily set up, hit this very top button here, New Simulation for the UK, and that brings us to Form 1. Now, there are these things called simulation names or model names, and those names are names that you need to give the respective simulation so that the model has a name into which it should store the associated results. If you don't enter a name, the front end will actually give you a warning and say, that you should enter a run name or simulation name. So you can enter anything you like. It can, so long as it's alphanumeric, and I think it allows for various special characters as well. But let's just stick to something simple for the moment, like temp or test, for example. Now, when you enter things into these user forms, these boxes and indeed the check boxes as well, so there are check boxes that you can tick on and off. Some things will enable features, other things will disable them. For example, when we click on this box, it doesn't make sense for you to alter these boxes, so they're grayed out. If this box isn't ticked, then you may want to implement either one of these boxes, so they stay enabled. But whatever changes you make in these user forms are then translated into changes in the input sheet of your respective Excel file. So we've got a test here under simulation name. We might, for example, want year, 3000 rather than 2040 under the end year for the simulation, for example. And we might, for example, want a relative risk aversion of 3, let's say, really high risk aversion. Then we hit enter, and once we hit enter, the model then says, okay, I'll take those parameters and I'll throw them into the input sheet. Now if we hit the back button, we'll see that these values, at least except for the simulation name, are preserved. So the relative risk aversion is still 3, and the end year for the simulation is still 3000 rather than 2040. But when this back button allows you to correct errors or changes that you wish you had have made in preceding form. So hitting enter basically brings you forward through this user form structure, and eventually will allow you to get all the way to the end to run a particular simulation. As I say, I'm not going to go through all of these user forms and what they do. One general point to note, however, is that if anything is odd or appears less than obvious, very often you may find that there's this little question mark box, and that provides some additional detail about the respective options and what you might choose and why you might choose alternatives. So that's the user form structure. You can either walk through one by one through the user forms, or you can jump very often through to the end, which takes us to this final simulation box. Now, there are two things really. I'm not going to walk through this user box, this form in detail here, but there are two things that you are likely to want to be thinking about here. You can either launch the model by pressing this button here, and that one is highlighted by default, and if you press that, the Excel file will save, and then the macro that's embedded underneath this user form will find the SIDD executable and launch it for you. Or you can press this exit button, and in the first, when you're first starting to use this model, I encourage you to press this exit button rather than the launch model button, for reasons that will become evident now. So if we hit exit, what's happened here is that the user front end has been used to set some differences in the model parameters up, but we haven't started running the model yet. This gives us a chance to look at the different changes that we have implemented through the front end and see whether actually we really want those changes to be made. So you'll recall that we set up a name called temp for our particular simulation. That's found in cell A2 here. If we look at the check sheet, there are 8 differences between the base and the respective, so the base parameters, which are stored in input A, and the input sheet that the model will reference when it's actually trying to run. So if we run through those differences first, you'll see that there is one difference in column Y, row 2. And so if we look at that, column Y, row 2, under the base specification, input A was 1.55. Under the alternative that we've set up is 3. Recall that we set this to a high relative risk aversion of 3 in the user form. So the check sheet has helped us there to find the relative risk aversion parameter that's embedded in this Excel file. So that's the first difference, but there are still 7 more differences to go. So if we look across the row here, we can see there's all zeros, keep going, all zeros, all zeros, all zeros, until there's 6 differences here in column BQ. So if we look at column BQ, just basically stepping horizontally through the Excel file, that's input A, and here is input. So the key here to note is that up the very top of the column here in BP, it says analysis params. Now basically these are parameters that are all involved with running secondary analyses for the model output. So basically there are 3 stages in any simulation. Well, 4 stages actually. The first stage involves setting the parameters up. So that's basically what we're walking through now. The second stage involves solving for lifetime decision problems. Now, for the solutions to the lifetime decision problem. The third stage involves actually projecting a population, an evolving population cross-section based upon the solutions to the lifetime decision problems. And then the fourth and final stage, is to analyze the output that are generated by from that population projection, and the parameters governing that fourth and final stage are all in this this column BQ with values defined in column BP. Now there are differences identified there in this check sheet, primarily because when the model comes delivered, it comes delivered to run all set up to run a base specification. And that base specification actually involves a bunch of secondary outputs that are pre-selected for you to check whether the base has actually generated something that looks reasonable. And so because we didn't implement the same secondary analyses in when we walk through the user forms, all of those pre-loaded tests for the simulation base have been turned off, and that's effectively what these 6 things are indicating. And indeed, you can see that all 6 are related to the first few rows of column BQ. And what these rows are actually doing is implementing a bunch of cross-sectional mean, calculating a series of high-level moments for selected population cross-sections, so that you can look at these outputs and consider whether they are reasonable or not. And we'll get to that in a moment. So we have 8 differences. We found 1 difference in column Y, 6 differences in column BQ, and that leaves 1 difference to be found, and that's in column BU row 5. So if we go to BU row 5, that value was originally 30, and in our change it's 990, and that's primarily because it says number of periods to simulate forward. Effectively, this is defining the ultimate simulation horizon. The original specification is delivered to project through to 2040, which is a 30-year horizon from 2011. We changed that 2040 to 3000, which is a 990-year horizon from 2011. So they're the differences that exist between the base specification and the alternative that we defined through the front end. Now, there are this setup provides a really useful way of looking at things. So if we save that, in order to run this specification, we need to save it first. So we simply save this file, and then to run it, we go to the main model subdirectory, and we just double-click on this SIDD.executable file. Now, the first thing that this SIDD executable does is it loads in all these parameters. It then performs a check on the parameters to determine whether they're reasonable or not. And if they're not reasonable, it will either alter them internally to make them reasonable, or it will tell you that the current specification just won't work and you need to change it. And the reason that the specification that we've got here is useful is that it actually involves an oddity, and the model will show us what that oddity is. So stepping through, you can see it loads up an initial set of commands basically telling you what version of the model you're running, some MPI stuff that basically tells you that you're running one task on the current computer. And then it says, okay, I'm running this job temp. This is the name that we gave to our simulation, you'll recall. And then it says, oh, you know, there's this warning stuff, and this warning stuff is saying a bunch of material about the fact that the birth cohorts that are set up by definition are inconsistent with the time frame over which where our simulated horizon is projecting. So it then tells you, okay, I'm fixing this up, and it gives you some description about how it's fixing that up. Following that warning message, it then starts. It does some preliminaries, and those preliminaries effectively involve setting up a place to save the output and saving all the parameters so that you can replicate the respective output or the respective simulation. Having done that, it then jumps into solving the lifetime decision problem, and here it's stepping through using backward induction to solve the lifetime decision problem, starting at age 130, which is our highest age. If you go up here, age 130, it took 1.552 seconds to define that lifetime decision problem solution, and it's stepping backwards through time, age 100, 99, and so on, all the way back to the first age that we're assuming the adult lifetime begins at, which is defined here in cell Y7 as 18. So basically this will just simulate backwards through time, or backwards through the life course to age 18, and get a full solution to the lifetime decision problem. So that's like the second step of the 4 steps that I outlined earlier in this tutorial. We did the first step through the front end, and this is stepping through the lifetime decision problem. It will then run, set up projections for the simulated population cross-section before finally generating secondary analytical statistics for the respective simulation. This isn't a simulation we want to run because A, the population projection is just going too far into the future, and B, the relative risk reversion is just really way too high. So let's close this off. The final thing that that is likely to be of immediate interest following this temporary simulation is actually what's being produced. So, as I say, the simulation started off by loading in parameters, then checked those parameters, and then it saved a whole bunch of stuff. And it saves the stuff, all of the output associated with a particular simulation in this simulations subdirectory here of the model directory. If we go into that simulation subdirectory, you'll see that there are 2 here, one of which has this name temp, which is the name that we gave that simulation. If we go into there, we'll see that there are a whole bunch of parameter Excel files that are saved into this subdirectory, and these Excel files contain all of the parameters that are necessary in order to replicate the particular simulation. It also includes 2 subdirectories, which are working directories, and I'm not going to discuss those in this tutorial. So that's all the stuff that that we can really get out of this initial temporary simulation. So I'll just close that down. Now, and I'll delete the temporary simulation subdirectory from my my simulations folder. So, as I say, you run the simulation, it generates a solution to the lifetime decision problem, and then it projects the population through time. And this can all take quite some time. When it completes, it'll come up with a window like this. Now, this is something that I ran earlier. Basically, the final message that you should find. It will either generate new the final message that you should get is something like this. It'll give you the proportion of the population that's not captured. Now, the simulation is actually projecting from a reference cross-section. And the characteristics of some of those individuals in the reference cross-section might not be perfectly captured by the model structure. And this first line is basically saying that 1.8% of the population that is loaded into the model as a reference from which projections are supposed to be made, were not perfectly captured by the model structure. It then tells you that the evolving cross-section, population cross-section, is projected to a particular time horizon. Here it's to 2040. It completed the simulation population. It's saving the output. And then it completed the population generation in 263 minutes. Now that's for the full simulation, including the solution to the lifetime decision problem. And then it completed the full model run of the particular simulation name, 2011p_base, in 330 minutes. And it says, okay, I've completed all the simulations you asked me for. Please press enter to exit. Before that, these lines of output are basically the lines of output that are generated when the model is projecting the population forward through time. So if you ask the model to project a population backward through time, it starts with the backward projections and then gets onto the forward projections. So we've asked for the model to project forward 30 years from 2011. And you can see that there is a projecting data for 2011, 12, 13, 14, and it basically projects this stuff as the simulation is proceeding. Before that, it's actually the same simulation was asked to project the reference cross-section backward 68 years through time, and this is done in order to build up a complete life history for each individual represented in the reference cross-section, and these lines of output are effectively providing details about how that projection was managed. So that's all of the output that you should see in your executable window. If the model encounters a problem, it may provide an error. If you find that this window shuts without you actually asking it to close, then there's been some sort of problem, a catastrophic error, if you like, and the model has just closed by itself. And you should let us know if you ever find something like that. And if the model has found a problem but it's been able to keep running and get to the end, it will restate the whatever error codes at the end, so that you don't have to check right at the top to make sure that nothing went wrong. So basically there's a reminder, if you like, of any errors that are encountered. And please let us know if you find any of these errors, and indeed please let us know if you find any of these errors and you manage to solve them and you manage to get on with things, because really the purpose of making this thing available online is to get rid of those whatever errors remain and help everybody who's currently using the model in the process. So that's the executable window. So we'll just close that. You can close it by either clicking the cross or hitting enter, and then we'll quickly go through the output that's been generated in this simulation directory. Recall that the base specification uses a name for the simulation called 2011p_base, so that's in the simulation subdirectory. If we open that up, it includes a whole bunch of material. If we order by type here, we can get the Excel files right up the top. Now, the model loads in parameters from Excel, and it generates secondary outputs to Excel. Unfortunately, there's a problem that's known by Intel, and I suppose they're trying to work on fixing it with the communications with Excel. So actually, we've had to suppress the communication with Excel, at least in the output phase at present. And so if we look at some of these output files here, for example, this 2011p underscore base 2011 CS file, which is highly cryptic, I suppose, is actually one of those 5 simulation files that we noted earlier were being emitted from our test simulation, but are projected in this this base specification. So if we open that up, you get a file that's all set up. It just needs the simulated outputs. So if you to get the simulated outputs, we hit Alt and F8 to bring up our macros window, and we run this update data macro, and basically that just pulls in the data that was simulated and output from the model, and this is for the 2011 population cross section. Here we have outputs for employment, moments by age, so rates of full-time employment among single adults and among adults in couples, non-employment for the 2, employment income, moments for employment income, means and variances, disposable income, again means, age-specific means and variances, consumption, means, again, variances, and pension participation. So basically each of these files that are saved in this base directory here produces the same set of outputs, but for different time horizons. So this is 1985, 2001, 2020, and 2035. With the extension CS referring to cross-section, because you can just as easily generate these outputs for lifetime of a particular birth cohort. So they're the Excel output files, and they all sort of work in the same way. So high-level statistics, poverty analysis, they're all output, simulation output, or secondary simulation output, if you like. The long file, well, actually, before we get on to that, the other Excel files in this subdirectory are all parameter files, which I noted in relation to our test simulation. There's a couple of data files up here, which are reference files defining the terms of the population. They're really working files that you don't need to worry about much. And then there are these CSV files. Now, these CSV files are the panel data that are generated by the model. They're output in standard CSV format, which you can open by double-clicking into Excel. If we open one of those up, basically these files report the circumstances of simulated individuals. So if we if I change the format along to read numbers rather than letters along the top here. Each row corresponds to a simulated individual, each additional column to a simulated time period. Now, you'll recall that the model was projecting backwards 69 years, I think. 68 years. So look, just to confirm that, if we double click on the job file, we can go to cell 73(6), and it's 68 years backward in time. That means that our reference cross-section is in period 69 So if we go to 69, you can see there's an age pretty much for everybody, at least at the top of this this population here. Now, the model is projected forward and backward through time for each of these individuals. So for the first individual here, they were 37 in the reference cross-section. They're 36 in the year prior to the reference cross-section, 35, 34, 33. And similarly, 38, 39, 40. And if we go all the way across, we can see that they're still not dead by the simulated time horizon. In contrast, individual 4 was aged 73 in the reference cross-section, and they're projected to die at age 85, or at simulated period 81. Now, so each row is an individual, each column is a time period, and you can see that our total simulated population is comprised of 89,611 people, and this last group really comprise, well, the last bunch comprise a bunch of people who are, aged above 18 generally, and these are all immigrants into the simulated population. If we keep going up, then you find a whole bunch of people with age 18. These are maturing children into the population, and then eventually we get up to people who entered in the penultimate simulated period. So immigrants who entered in the penultimate simulated period, and then again they will end up getting, if we keep going up, we find children who matured in the penultimate period and became age 19 in the final simulated period through time. So that's that's the structure of these CSV files, and they can be extremely useful for eyeballing the simulated data, making sure that they make sense, making sure that they're generating the kind of effects that you're interested in. The only other thing to mention here is this long file. Now, the long file output is identical to the CSV output, except it's been optimized for importing into Stata. So by default, this option is enabled, and if you prefer to look at simulated output using Stata rather than Excel, then you'll find that these long file data variables are preferable for that purpose. So that's it really. So we've walked through how to set up model parameters through the front end or through the input file of the job file spreadsheet. How to run the model. What the model does when it's running, it's generating solutions to the lifetime decision problem using backward induction, and then projecting the simulated population forward and backward through time. And then we've walked through the simulated output, both the microdata and some of the secondary data analysis outputs. Hope you enjoyed this tutorial. Comments very welcome, and I will see you next time.